in the course in Chapter 7, you'll find the Chapter 7 study guide. I give you a copy of it, and I want to go over some stuff that's actually on the first 2 pages of the study guide. So if you have it, I can help you get stuff filled out so you understand stuff. In the plan for the week, so I want to tell you about different ways that ocean currents are measured today and show you some good applications of that. And tomorrow I'll tell you some stuff about El Nino. You may have heard of El Nino as a like a weather / climate thing. So there are changes in ocean currents that affect weather on a medium to long term scale. And we'll do some stuff with El Nino on Tuesday and Wednesday. And there's a thing about El Nino that's due on Thursday. I'll tell you about it tomorrow. Anyway, so if you're remote, I have some links here. Under the plan for the week, there's a thing that says methods for measuring ocean currents. And this thing that says methods for measuring ocean currents. There are a few different videos here, like this one and this one. And it's best if you watch them like on your own. So in the Chapter 7 folder, there's a thing that says method for measuring ocean currents. So let me show you first about like ideas about surface currents and ocean currents. So if you're remote, that's a good link to follow there. I'll play it on the middle screen. Up here, sounds pretty good. I got some new speakers, they're pretty pimp. There's like an ad, but we gotta wait for the ad. Yep. Okay. Okay. Yeah. I'll give you the stuff tomorrow and whenever it's good.
In 1992, a cargo ship carrying bath toys got caught in a storm. Shipping containers washed overboard, and the waves swept 28,000 rubber ducks and other toys into the North Pacific. But they didn't stick together. Quite the opposite. The ducks have since washed up all over the world, and researchers have used their paths to chart a better understanding of ocean currents. Ocean currents are driven by a range of sources: the wind, tides, changes in water density, and the rotation of the Earth. The topography of the ocean floor and the shoreline modifies those motions, causing currents to speed up, slow down, or change direction. Ocean currents fall into 2 main categories: surface currents and deep ocean currents. Surface currents control the motion of the top 10% of the ocean's water, while deep ocean currents mobilize the other 90%. Though they have different causes, surface and deep ocean currents influence each other in an intricate dance that keeps the entire ocean moving. Near the shore, surface currents are driven by both the wind and tides, which draw water back and forth as the water level falls and rises. Meanwhile, in the open ocean, wind is the major force behind surface currents. As wind blows over the ocean, it drags the top layers of water along with it. That moving water pulls on the layers underneath, and those pull on the ones beneath them. In fact, water as deep as 400 meters is still affected by the wind at the ocean surface. If you zoom out to look at the patterns of surface currents all over the Earth, you'll see that they form big loops called gyres, which travel clockwise in the northern hemisphere and counterclockwise in the southern hemisphere. That's because of the way the Earth's rotation affects the wind patterns that give rise to these currents. If the Earth didn't rotate, air and water would simply move back and forth between low pressure at the equator and high pressure at the poles. But as the Earth spins, air moving from the equator to the North Pole is deflected eastward, and air moving back down is deflected westward. The mirror image happens in the southern hemisphere, so that the major streams of wind form loop-like patterns around the ocean basins. This is called the Coriolis Effect. The winds push the ocean beneath them into the same rotating gyres, and because water holds on to heat more effectively than air, these currents help redistribute warmth around the globe. Unlike surface currents, deep ocean currents are driven primarily by changes in the density of seawater. As water moves towards the North Pole, it gets colder. It also has a higher concentration of salt, because the ice crystals that form trap water while leaving salt behind. This cold, salty water is more dense, so it sinks, and warmer surface water takes its place, setting up a vertical current called thermohaline circulation. Thermohaline circulation of deep water and wind-driven surface currents combine to form a winding loop called the global conveyor belt. As water moves from the depths of the ocean to the surface, it carries nutrients that nourish the microorganisms which form the base of many ocean food chains. The global conveyor belt is the longest current in the world, snaking all around the globe, but it only moves a few centimeters per second. It could take a drop of water 1,000 years to make the full trip. However, rising sea temperatures are causing the conveyor belt to seemingly slow down. Models show this causing havoc with weather systems on both sides of the Atlantic, and no one knows what would happen if it continues to slow or if it stopped altogether. The only way we'll be able to forecast correctly and prepare accordingly will be to continue to study currents and the powerful forces that shape them. What about the...
All right. So the next one I want to show you is actually about the Gulf Stream. So a specific current that's important, that we've already seen some stuff about, is this Gulf Stream current, which flows from really the southern Caribbean up through the Gulf of Mexico and up along the eastern United States. But it continues across the Atlantic Ocean and up to northern Europe. So here's a thing, a bit of like geography trivia. If you draw a line, this line of latitude right here, let me, I can get a straight line on this thing. Oh, my straight line tool's not on there. Anyway, see this line of latitude? You draw this line of latitude straight across. Every part of the continental United States is below that line, but all of England is above that line. Most of England, the British Isles, is the same latitude as much of like central Quebec and Ontario and the central Canadian provinces. When you think of England, you probably don't think of like heavy snowstorms and really cold winters. It's because they don't have them. It can snow in England, and they do get snow from time to time, but it's not particularly cold. Like it's a, you know, they get a lot of rainfall, but they don't have really, really, really super cold winters. But even, you know, down into the Appalachian Mountains, well down into West Virginia and Virginia, you can get heavy snowfall in the wintertime, but very, very infrequent snowfall in the British Isles. And it's in large part because of this Gulf Stream current, which carries warm water not only up along the east coast of the United States, but all the way across into like England. So England, Ireland, Scotland. Okay, so if you are remote, this next one here, the Gulf Stream Explained, that's the one I'll show now, because it has to do with, so keep that in mind about the role that Gulf Stream plays with Europe. So this video is actually made for audiences in Europe, but it's, you know, completely makes sense on a global scale. Ooh, there's an Apple event. What's it going to be?
The ocean conveyor belt and the Gulf Stream. Ocean currents have a direct influence on our lives. They determine our weather, our climate, and much more. The ocean currents and wind systems transport heat from the equator to the poles and operate like a large engine for the global climate. In the oceans, there are numerous currents. The so-called ocean conveyor belt is very important for our climate. This term describes a combination of currents that result in 4 of the 5 global oceans exchanging water with each other. They form a worldwide circulation system. The conveyor belt is also called the thermohaline circulation, with thermo referring to the temperature and haline to the salt content of the water. Both determine the density of the water. While the masses of water may be moved in part by wind, primarily the different densities of the global oceans are responsible for their movement. Warm water has a lower density and rises, while cold water sinks. The water's density also increases with a higher salt content. At the equator, the heat from the sun is especially strong, resulting in a lot of evaporation and thus a rise in the water's salt content. That is where the Gulf Stream begins. The Gulf Stream is very important for the European climate. Its length of 10,000 kilometers makes it one of the largest and fastest ocean currents on Earth, and it's very warm. At roughly 2 meters a second, it brings up to 100 million cubic meters of water per second towards Europe. A constantly blowing wind, the southeast trade wind, drives warm surface water to the northwest into the Gulf of Mexico, where it heats up to 30 degrees Celsius. The turning of the Earth and the west winds then direct the Gulf Stream towards Europe and split it up. One part flows south, another east to the Canary Current, and a third part flows north, where it releases a lot of heat into the atmosphere as the North Atlantic Current. The water becomes colder there. Its salt content and density rise on account of evaporation, and it drops down between Greenland, Norway, and Iceland. There we also find the largest waterfall on Earth, roughly 15-kilometer wide pillars with water falling up to 4,000 meters, 17 million cubic meters of water per second, or roughly 15 times more water than is carried by all the rivers in the world. This creates a strong maelstrom which constantly pulls in new water, and is the reason that the Gulf Stream moves towards Europe. Countless species use the Gulf Stream as a means of transport on their trips from the Caribbean to northern areas. But it doesn't just bring us animals. An enormous quantity of warm air also comes with it. In order to produce the same heat which it brings to the shores of Europe, we would need 1 million nuclear power plants. That's why we also call the Gulf Stream a heat pump. Without it, the temperature would be significantly colder here, at least 5 to 10 degrees. Instead of lush fields, we would have long winters and sparse ice-covered landscapes in Europe. In the last few years, scientists and pundits in the media have repeatedly expressed the fear that the Gulf Stream could come to a standstill due to climate change. Because if the polar caps actually melt, the salt content in the water off Greenland would fall, as would its density. The North Atlantic current would no longer be heavy enough, and so it wouldn't sink as usual. In the worst case, that would bring the Gulf Stream, our heat pump, to a stop. Some climate experts also assume that climate change could compensate for this effect. We know that it can be normal for the climate to change by looking at the development of the Earth over the last few million years. There are ice ages and warm periods. In the last ice age, a gigantic flood of melting water crippled the heat-bringing North Atlantic current, covering the northern hemisphere in ice. Scientists have different views on the impact that climate change will have on the global ocean conveyor belt. But one thing is clear: when the climate changes, then the complex system of ocean currents and winds, which has remained fairly stable since the last ice age, will change in ways that we don't yet understand.
Okay. And then let's see. There's a really excellent animation. It's the next link in the thing. It'll be on both the side screens about relative ocean currents in and around Europe and the Mediterranean. So this is the Mediterranean Sea here. This is the southern part of Italy, the boot of Italy. And then this is the main Mediterranean Sea. This is France up here. Oop, France is here, Spain is there. So you can see the motion of the currents can be very complex within an ocean basin. There's a general flow of water into the Mediterranean Sea through the Strait of Gibraltar. So you may know, let's get to it. All right, so Nick snoring again. This is Portugal here, and this is Spain. This is Northern Africa. Water flows into the Mediterranean Sea through the Strait of Gibraltar. He's like sawing a log. He's like, hear him? It's pretty good. Anyway, so water flows in, and then it forms these gyres. A gyre is a localized current where there's motion as a result of differences in topography and whatnot. And then that water, when it flows into the Mediterranean Sea there, and then that could be from tidal action and it can flow back out, but it can also flow out of the Mediterranean and into the Indian Ocean through the Suez Canal. And places where there are restrictions oftentimes have very, very high current speeds. So another place that has a very high speed of current is the English Channel. And the English Channel's current changes direction. So up here between France and the British Isles, you'll see the density of the lines goes way up. And the direction of that current changes from heading north to heading south, depending upon the time of the month and the direction of the tides as a result of the pull of the sun and the moon. So there it's a northerly path, and then it changes and it's a southerly path. But the speed of the water through this narrow English Channel here can be very, very, very high in one direction or another. And sometimes it's like a slack speed or like slow. So, the distance from England to France isn't that great across this channel. It's a relatively narrow passage. Lots of shipping takes place through there. And then, I don't know, in the history of World War I and World War II, it was very important. So let's see. So the major devices for measuring ocean currents include measuring the motion of a thing that's floating in the water. So sometimes it's intentional, sometimes it's unintentional. For the unintentional things like the Nike shoes or the rubber duckies, it's kind of fortunate to oceanographers that we can study the motion of the path of those things. But we also build intentional drift buoys. And those drift buoys aren't just dumb things that you put into the water. Oftentimes, this is a good example of a Noaa drift buoy. There's a big plastic bag which hangs down into the water so that you're mostly measuring the motion of the water and not measuring the effect of the wind blowing on it. And then oftentimes you're not just going to measure the position, but you can also measure the salinity and the temperature, or maybe the pH of water. And then up here, be able to send location, temperature, salinity, maybe pH information by radio to a radio receiver, either for a passing ship or up to satellite. And then you can also recover the thing later. So the traditional method of measuring the motion of currents is to like throw something in the water and see which way it goes. Another common way that current speeds are measured is actually done through the shipping industry. And the Navy has done this technique, and it's a very common technique both in shipping with boats and also with aviation to figure out the speed of the wind or the speed of the water. You can compare the speed of the boat relative to the water to the speed of the boat relative to the planet. So for instance, here's a ship, maybe like a little cruise ship, and the cruise ship is moving along. And the propeller is propelling the ship in the water with a speed of 15 knots. So a knot is a speed that's about 1.2 miles per hour. Knot is a common unit of speed used in both aviation and in navigation by ship. So the boat thinks it's going 15 knots in the water, but whenever you use a GPS to measure the motion of the ship, the GPS says you're going 17 knots. So if you're heading in this direction in the water and your speed relative to the water is 15 knots, but the GPS says you're going 17, it's as if you've got like a 2-knot kind of like boost or advantage. And that must be because the water itself is moving maybe with a speed of 2 knots. So in other words, if you were to shut the propellers of the ship off, shut the engines off, the ship would still drift along with the current at a speed of 2 knots, and you don't even have to do any work. On the other hand, if the ship is steaming along with a speed relative to the water of 15 knots, but a GPS says that you're moving 13 knots relative to the planet, it must be because the current is heading in the opposite direction. So whether you're going into or away from a current that's 2 knots has a significant effect on the speed of that ship. If you're going in the same direction as the current, now you're going 17 instead of 15. If you're going the opposite direction, it's 13 instead of 17. And going 17 instead of 13 is a huge difference in speed and can give you a big advantage in time if you're trying to go all the way across the world's oceans. So lots of issues with navigation in plotting courses. are as a result of dealing with currents. So, for instance, if you're like, okay, I'm going to maybe leave New York and maybe sail to Cape Verde, maybe not sail, not a sailing boat, but a motor yacht, and you're going to travel from one place to the other, like when Jaden buys his like yacht on whatever site that is. If if as you travel from one place to the other, if the current is heading in the same direction, in the direction you're traveling, it will reduce your travel time. But if, on the other hand, the current from Cape Verde back to like New York is heading in that direction, you'd want to avoid the current by maybe taking a more circuitous path so that you're not directly in the current, or find a current that's going in the same direction. In a way, it's like a conveyor belt that can help you with navigation and travel. So it turns out that to oceanographers, it's very useful to learn about ocean currents for a lot of different reasons. But the practical way we know about the world's ocean currents and how we've measured them historically is from trying to save time and money in shipping stuff around the world. Okay, another way to measure ocean currents uh, that's more sophisticated is a project called Argo. So here's an issue. When you put a float on the surface of the ocean, the only thing that you're measuring is just the speed of the water at the surface. But like in the videos, and what's true and described in the textbook, is there are also currents deep in the ocean. And it could be that the surface water is moving to the east, but the water at great depth is either moving slower or more maybe moving to the north, moving in some other kind of direction. So if all you ever do is just measure the surface motion of the ocean current, you don't get a full picture of the motion of the water at all depths. So there's this project called Argo, and Argo uh, there's a good overview of Argo in that link right there. So if you're remote, this like Argo float project, how Argo's floats work, and Argo float map. I'll get to the map in just a minute. These two videos here I'll show in class right now because they show like how the whole thing works and the ships and the whole get up and go. All right, this one's pretty good. It's only like 2 minutes. Usually people have to be on their back to snore. He snores like right just like that. It's pretty savage.
Any studies of climate or immediate impacts of what's going on in the ocean at the time, so questions about fisheries or marine mammals or seabirds, we've used Argo for all of those sorts of studies. Argo's been a complete revolution to our knowledge of the ocean. Argo is an international collaboration of about 23 countries at the moment, deploying profiling drifting floats in all the world's oceans. Floats that freely drift around the ocean and profile down to 2,000 meters. So every 10 days from every float, you get the temperature and salinity down to 2,000 meters. Basically, the temperature is quite easy. It's measured with a thermistor. But the salinity is measured by measuring the conductivity really accurately. And then once you know the temperature, you can use the conductivity to calculate the salinity. They are pretty high-tech instruments on every single Argo float to achieve that. It's a huge advance for physical oceanography and for oceanography altogether, because in the old days, how you used to get that information was you had to take a ship out, lower a CTD through the water column. It was very expensive and very slow, whereas now you have this global network of floats. And since they report back via satellite, you have basically near real-time knowledge of the state of the ocean all around the world. It's very hard to deploy floats in the southern hemisphere because there just aren't enough commercial ships to deploy floats on. So that's where these charters of Coriolis come from. Now, at the moment, there's about 3,700 floats all around the world, and Coriolis to date has deployed over 1,100 floats in the southern hemisphere. Without that, we wouldn't have got global coverage. So NEMA and New Zealand really have been a big contributor to Argo, and that's recognised around the world.
Okay. Nick. Damn.
presently the ocean is really undersampled. We have big gaps in our knowledge, particularly around how the biology and chemistry interact with the physics and control things such as fisheries, phytoplankton, which ultimately impact the way the oceans function in terms of productivity, amount of food that they can produce, the way that carbon dioxide is absorbed by the oceans and take away to actually mitigate climate change.
So an Argo float is like a robot that is operating freely at sea. So it goes down to 1,000 meters. It sleeps for 10 days, and after that it goes down to 2,000 meters. And while he's going up, he's making measurement of temperature, pressure, and salinity up to the surface. When you arrive at the surface, then it transmits the data by satellite link directly to shore where the data are processed and delivered to the users.
So what Atlantis project and work that we've been involved in is actually creating better sensors that can go on these Argo floats, the so-called biogeochemical sensors that allow us to address the biological and chemical components of the ocean, not just the physical components such as temperature, salinity, and pressure.
Now our target is to have 1,000 of these robots operating globally in all the ocean so that we can have a complete picture of the ecosystem ocean.
What the Atlantis project has done is allowed us to make a step change in our ability to observe the oceans. By augmenting the Argo system using the Atlantis project as a pilot, we can show that we can observe our planet at a much better temporal and spatial resolution than we could before.
All right, so the plan, here, make sure that doesn't play something else. All right, so the plan is those floats are deployed, and because they have a satellite uplink, they can provide pretty much real-time data. Whenever they're submerged, of course, they can't provide data, but whenever they come back up, so you know where the thing's submerged, you know where it comes back up, and how it varies its depth is by taking water into a ballast tank. It makes it more dense, and then it expels water from the tank and fills it with a little compressed air, and the thing floats back up. All the while measuring differences in temperature on the way down, differences in salinity on the way down, and then back up. The bio-Argo floats also measure nitrate and phosphate concentration and magnesium and calcium in the water, which give you a better sense of differences in chemistry on the top and bottom. And they can be serviced. So whenever you know where whenever it runs low on battery power or needs to be serviced, you can find out its location because it has broadcast its GPS signal, but also has a small radio transmitter on board that you can just track the same way as you'd like track an animal with a radio tag or whatever like that. So here's the current Argo float system. So this is the Argo status. Let's see. So these are reported locations in the last 3 days. So this is all the Argos. Those are those floats that are deployed around the world's oceans that have reported their location within the past 3 days. So this is like the newest data itself. It's not a hot clickable map, but this one shows the current, the current location of all the ones that ought to be out there. So there's a total of 3,786 active floats. That's April, that's today. And those are the relative location of all the floats. So in a way, oceanographers around the world are able to know current temperature, salinity data from all those floats. And when they said that there are customers, just as an average person, you don't have access to that data. but world oceanography organizations like NOAA can get information. People who work in fisheries, so like if you're a large fishing, like a company that does offshore fishing, you want to be able to get as much data as you can to inform where you should go to find the greatest amount of catch using the least amount of fuel. And then whenever you're at Earth.null school, the way in which this site is able to display current and temperature information, it's like when you go to ocean current and sea surface temperature, whenever you're on this site and like you see, whatever the temperature of the water is, the sea surface, and the direction of the ocean currents, how it's possible to know this information in near real time. Because this says, let's see what the date is. This was as of uh, 8 Zulu yesterday, or 8 Universal Coordinated Time yesterday. So that's only like a day old data in terms of ocean temperatures and current direction and speed information. Is that data comes from the Argo uplinks. So you've got autonomous, robotic, temperature, salinity, depth, current measurement probes that then send their data up to satellite. Those satellite downlinks can then be used by oceanographic organizations and also be used to be able to see this information in real time. So you can't see the granular data. In other words, you can't know as just a regular consumer what the last position of an Argo thing was if you're not a subscriber to the network. But to the general public, there's good overview information. It's also used by meteorological organizations to figure out like, the propensity for an El Nino event to take place, or if you're trying to do some kind of weather forecasting, maybe here in North Carolina, uh, and you're a little bit unsure about what the coastal temperature is going to be. What would be useful is to see like what the speed of the Gulf Stream is, because if the Gulf Stream is relatively fast, carrying a high volume of water, and it's expected to increase, then that would encourage the temperature here to be higher. If instead you're at a period of time with the Gulf Stream having a reduction in speed or reduction in current, you would expect the temperature here to be relatively lower because there's a lot of heat that's delivered by the Gulf Stream. Or maybe on the West Coast, the Japan current famously flows. It's called the Japan current because there's a cold current which flows from Japan. Well, it's actually pretty slow up along the Aleutian Islands, but there's a relatively cool water current which is cooled by the North Pacific as it comes across the Pacific Ocean toward the west coast of the United States. It's actually pretty diminished right now. And that's what keeps the water relatively cool on the west coast, because all that water has spent a lot of time in the North Pacific, traveling across the North Pacific toward the west coast of the United States. That's why we have comparatively cooler temperatures of the water on the west coast as compared to the east coast. And we also have much milder currents on the west coast right now as compared to on the east coast. This is a pretty fast Gulf Stream speed right now. So those are the major ways in which ocean current speeds are measured. The last like example, so you actively measure ocean currents using intentional float devices or bottles, which you say, hey, here's the location and the speed, or here's the location and the time and the date when I drop the thing off. Then you pick it up or you find it later and have it broadcast information on the surface. You can measure speeds of currents on the surface by comparing the speed of the boat relative to the water to the speed of the boat relative to land, and derive from that like what direction and the speed of the current must be. Argo is the most expensive and sophisticated things. A lot of times those floats are deployed. Sometimes they can be deployed on research vessels, but then also like if you're in NOAA, the National Oceanographic Atmospheric Administration, and you want to deploy another 15, Argo sensors, you may contract with a fishing fleet and say, hey, you guys are heading out from maybe Seattle, you're heading out into the Pacific Ocean to the approximate location where we want to deploy them. Then on board the fishing vessel, they may have scientists who are going to do the deployment. So like, hey, while you guys are out there doing your fishing, can we hitch a ride? We're going to throw so many things in the water, and then you just bring us back to port like whenever you're done. Because research ships are very, very expensive to operate. The last method is the unintentional measurement of ocean currents by Flotsam, like in the Nike Shoes Lab, to just say, hey, sometimes some crap ends up in the water. Maybe it's trash. Maybe it's stuff that got thrown overboard off a ship. We know where and when it was released. And then tracking the position and motion of that stuff lets you know about the direction of the currents. Another example, so MH, was it 470? I think that's the number. 370. Let's see if we can find. I guess that one's okay. Yeah. So I mentioned this before. This came up, I don't know in what context or whatever, but there's maybe about ocean depth and how broad the ocean is. There's an aircraft, a Malaysian Airlines aircraft, MH370, which just disappeared quite a few years ago. And so it took off from Kuala Lumpur, Malaysia, heading toward the northeast, lost radar contact here. But then there's a good probability that it crashed, or it crashed in the ocean somewhere along this path. That's from data from satellite uplink from engine monitoring information. And there's some debris that was found off the coast of Madagascar, Reunion Island, which is from that aircraft. This was about 6 years ago. It washed up, and that makes an awful lot of sense because if the plane crashed into the ocean in this region here, which is like the northernmost part of this possible search area, debris on the ocean surface, seats, flotation devices, any kind of passenger effects that float on the ocean, that floating debris will be carried by ocean currents. There is an ocean current which heads, through uh, between the Micronesian Islands and Australia, heading toward the west, heading toward Madagascar, and then going down around southern Africa. But debris from this is likely to continue to wash up along Reunion Island, Madagascar, the west coast of Africa. And the more debris you find, and if you're very sure about the location and the time that it washes up, it gets you better information about the possible location where the plane went down. Unfortunately, even if the plane went down here, it's possible for the debris to end up there because there's a current which flows up to the north and then to the west. But if you know the speed of the current and you know the relative time it took for the absolute time it took for the debris to move, you can determine like a probability of where the plane would have crashed along that location. It's possible we may never find that plane, but it's also possible that it will be found. The problem is when an airplane hits the water, particularly at high speed, most of it ends up just getting broken up into lots of little pieces, and most of the stuff sinks the ocean floor. So you're not looking for like a big long fuselage of an airplane. That's not going to still be intact. Instead, the whole thing's probably going to be all broken up. So I don't know if you saw, this is kind of, it's unrelated, but there's a pilot who had to ditch a plane off Cocoa Beach yesterday. And he's okay. But Cocoa Beach, Florida, there was an air show, and it was mostly like older aircraft. And this is a TBM. It's a plane that was used as a dive bomber, torpedo bomber, navigation aircraft in World War II and then after World War II. And the pilot ran into trouble. So here's the plane. The pilot ran into trouble and was too low, couldn't make it back to the airfield. So he needed to ditch. And the only reasonable place to ditch was on the beach or in the water. And the beach was like full of people. So it's really disappointing when people are like sunbathing and then you hit them with a plane. So you're trying to like, the pilot has to make a quick decision as to how to put the plane down somewhere so it's as safe as possible for people on land and as safe as possible for the pilot himself, and then also try to consider his own rescue and the possible salvage of the airplane. So this is about as good as you get. He came in, and then look, there's like people right here, right? You imagine being out swimming, and then this plane's like this, and you're like, what the heck is they doing so low? And the pilot ditched the plane, flew right over the heads of some people, and put it down. And then the pilot was okay, got out, and they salvaged the airplane. Look at the beach full of people. Isn't that nuts? So it's the right thing to put it in the water. Like if the beach was empty of people, putting it on land would have been a good idea. You could have just belly landed it on the sand. Except if you would have brought it down where people are here, he would have just killed a couple dozen people or something like that. But yeah, he made it. He was okay. Yeah. So this plane, the TBM, is well, when I first heard it was a TBM, and it went down in the water. First thing I thought of was, well, I know a famous case of that. President George H.W. Bush, the first President Bush, he ditched a TBM, the same plane, when he was a pilot, and he survived. The other two members of the crew passed away, but if it's not survivable to water land a TBM, then we wouldn't have two of the presidents we've had because both George H.W. Bush and his son George W. Bush wouldn't have been presidents if President George H.W. Bush hadn't survived the crash. So yeah, that's common. The plane, it goes down real quick, but this was in real shallow water, so they were able to secure it. They'll haul it back up. They'll be able to recondition the plane because those planes, they're World War II vintage planes. They have an incredible value. It's planes worth $1 million or more, worth a whole lot of money. So it's going to be a big mess because the whole thing's been inundated with salt water. So they're going to have to pretty much disassemble the whole plane. The props all got bent because when propellers are spinning, you hit the water, it bends the propellers. The propellers are toast. Could do damage to the engine, but the rest of the plane made it. The pilot got out okay. So I don't know. Is there a different? This is a different video. Here's another one. Yeah, that's not any better. Oh, can't see the plane. Your head's in the way. Oh, there we go. And the longer it sits there, as the waves crash around it, the sand, it'll kind of bury itself in sand. So they're gonna have to get that out of there.